Alright, we are going to be looking at X-ray crystallography. X-ray crystallography. Now, X-ray crystallography is a technique that is used to determine the three-dimensional structure, of proteins and other biomolecules. So the underlying word here is that X-ray crystallography is used to determine the what? Three-dimensional structure of crystals. There's a rule there. Any substance you want to determine the three-dimensional structure, that substance must be what? A crystal, right? You cannot use it for liquid. Cannot use it for gases. Any stuff you're using must be a what? A crystal. A crystalline substance. Now, how many of you have seen? You've seen salt, right? Your normal salt. There are some salts that if you touch it, it's just like it's powder. It's like there's no seed inside. If you pour water on that salt and evaporate the water, you see that you have seed, right? That's an example of a crystal. That's seed. That's the crystal. Now, X-ray crystallography is used to determine the three-dimensional structure of proteins and other biomolecules. Now, what is the principle here? X-ray crystallography works based on the principle that when X-rays pass through a crystal, that the X-ray interacts with the electrons surrounding that crystal. And as they interact with the electrons surrounding the crystal, the X-ray is diffracted into a specific pattern that can be used to determine the three-dimensional structure. I'll use this to explain that. Now, this is a crystal. We want to study the structure. Now, this crystal will pass X-ray through it. And one common source of our X-ray is synchrotron. So, synchrotron. Now, this X-radiation, this X-ray here, as it passes through this crystal have electrons arranged differently, depending on the type of the crystal. Now, as the X-ray passes through the crystal, it will interact with these electrons surrounding the crystal. And just as the light is coming through this, the light will just hit one crystal and one electron. If it is electron, it will, when it still continue in direct path, it will bend, right? It will be different diffraction, bending of light when it hits an obstacle. So the X-ray will interact with the electrons found on these crystal lattice, and it will be diffracted into a specific pattern, depending on how the electrons are arranged in that crystal. Now, we have an X-ray detector here that will detect the diffraction. But you seeing that on the screen, you cannot use it to interpret anything. So we have computer and graphics here that will be able to convert it into what you can use to interpret. From there, electron density map is formed. Now, this is it. As the X-ray passes through this, it will interact with the electrons, right? And as it interacts with the electron, what will happen is different patterns will be formed. A specific pattern will be formed. And that specific pattern, from our computer graphics, we can use it to get the electron density map. Electron density map is, these are the electrons. This is where it's concentrated. Here there's no electron. Here there's electron, like that. Now, from the electron density map, we can use the electron density map to determine the three-dimensional structure of the crystal. Or here we say the protein model, we're using the protein. But you can use it for any other crystal. So basically, X-ray crystallography works based on the principle that when X-ray passes through a crystal, the X-ray will interact with what? Electrons, right? Surrounding the crystal. And they'll be diffracted into a specific pattern, is it not? Yeah. It's just like in the night, you shine torch. Yeah. And if you shine torch on something, if I shine torch here, if the light is moving through this, as it hits this thing, it will bend, right? Yes. Is it not? There's something we used to play when we were small, when we were younger. stay in the house, inside house, open door, when sun is shining very well, we shine touch on the mirror in the house and be directing it to somebody's eyes outside. I don't know if you did that. I was what? You done once and that you. Alright, so this bending of light when it hits obstacle is what we call what? Diffraction, right? So as the X-ray interacts with the crystal, the electron surrounding the crystal, they'll be diffracted into different patterns. And different crystals have different arrangements of electrons. So with the pattern of electron, there will be a specific pattern of diffraction. We have X-ray detector that will detect the X-ray here that is being diffracted. So that diffracted X-ray will be analyzed by computer screen, by computer graphics, turning into something you see, electron density map. You can actually see this electron density map on the screen. But still, you cannot use it to say, okay, this is the molecule, this is this. But from the electron density map, we can use it to determine our three-dimensional structure. Now, if you have an unknown substance, let's say those persons working in the airport, and they saw an unknown substance, you're arguing it's drug, it's not drug, it's drug, it's not drug. They can actually use X-ray crystallography to study the shape of the three-dimensional shape of that molecule. Once they study the three-dimensional shape, they can know what it is. Now, the application, where can you use X-ray crystallography? You know that X-ray crystallography, we want to use it to determine the three-dimensional structure. And if you can determine the three-dimensional structure of that substance, we can actually tell what the compound is. So what is the application of X-ray crystallography? So it has been used to determine the three-dimensional shape of different biomolecules, proteins. Now, do you know that most things in our body have receptors? And you want to make drugs that are competitive inhibitors. The drug, the molecule, must have the same shape as the receptor, right? So that it can bind. So now, what will you use to study the shape of that receptor? You can use X-ray crystallography to study the three-dimensional shape of that. You can also use it to study the three-dimensional shape of enzyme active sites, protein-protein interaction. So you can use it in drug discovery. How can you use it in drug discovery? How can you use it in drug discovery? By studying the shape of targeted sites. By the time you study the shape, you can actually know the molecule you make that can interact with that shape of the receptor there. So X-ray crystallography is used in drug. I've said something. I've said it's used in studying the three-dimensional structure of molecules like proteins. Can be used in drug discovery. Now, it can also be used in geology. Who can tell me how X-ray crystallography can be used in geology? Geology, we are studying what? Eh? Okay, it's a soil, rock, study of the earth, Abi. Geo means earth now. Is it not? Geography, description of the earth. Yes. Geology, logy, study of the earth. But now we're looking at maybe solid soil, rocks, and rest. So what can you use X-ray crystallography? You can still use it to probe into the spatial arrangement of those crystals, rocks. You can use X-ray crystallography in forensic. I know forensic is involved in investigation, right? Crime investigation. If you see an unknown substance, you can use X-ray crystallography to determine the three-dimensional structure. And once you know the three-dimensional structure, you can know the name of that substance. Do you understand? Now, from this, X-ray crystallography obeys the Lambert's law. I will say the Lambert's law states that what? The absorbance of the light absorbing material is directly proportional to what? The concentration of the solute and what? And the mass length. Now, this Beer-Lambert's law is actually a combination of two laws, Beer's law and Lambert's law. So when you put two of them together, you have the Beer-Lambert's law. And putting the two together, it says that I want to relate to that crystallography. It says that the absorbance of the light absorbing material is directly proportional to the concentration of the what? The solute in that light absorbing material. If it is the X-ray crystallography, now we look at the crystal. So the absorbance is directly proportional to the concentration of the crystal. And also the what? Path length of the light travels. So if you want to remove this constant here, this is probability sign here will reduce the constant, right? Yes. It's equal to epsilon CL. So we use epsilon here to represent that. So basically, it obeys the Lambert's law.